Greetings to all. In this lecture, we will see the output VI characteristics of a power transistor. We already discussed about the power BJTs, where there are two types, NPN transistors and PNP transistors. And we saw the constructional features of a power BJT. And now, the output IV characteristics of a power transistor. So the given figure shows a typical output characteristics of an NPN type power transistor. So as shown in the figure, a power transistor also exhibits cutoff, active and saturation regions in its operation or in its output characteristics. So we can see the cutoff region here, active region and the saturation region here. So for the power transistor, there are two saturation regions. One is a quasi-saturation region and a hard saturation region. We will discuss these in this lecture. Okay, so we will see the cutoff region first. In the cutoff region, where the base current is less than or equal to 0, where the base current, which is the input current, is less than or equal to 0. In that particular time, the output collector current will be almost equal to 0. That particular situation is called the cutoff region. So the maximum voltage between the collector and emitter, where we take the output voltage, that is across the collector and emitter. The maximum voltage between the collector and emitter under this condition is called maximum forward blocking voltage, or it is called VCEO, maximum forward blocking voltage. Okay, that is about the cutoff region. The cutoff region acts when the IB is less than or equal to 0. Okay, now the active region. In the active region, the ratio of collector current to the base current, that is beta. Beta is the ratio of collector current to the base current, that is beta is equal to IC by IB. It remains almost constant. It is the current amplification factor or current gain. It is almost constant up to certain values. After that, it falls rapidly. So we can see that in the figure, when the base current or the input current is above 0, or it is IB1, IB2, different values. So the collector current also increases until a particular value, and then it drops or it falls rapidly. Typically, the value of the DC current gain of a power transistor is much smaller compared to a signal level transistor. That is, the beta value of power transistors are very less compared to the beta values of signal transistors. Okay. Again, now we will see in the active region, we can see the power dissipation limit, which is represented here, and it is the total power dissipation limit. Now as we go up or as we increase the base current, we can see a second breakdown limit here. Okay. So at higher levels of collector currents, the allowable active region is further restricted by a potential failure mode called the second breakdown. That is, the active region is restricted when the base current is higher, and that is called the second breakdown region. It appears on the output characteristics of the BJT as a drop in the collector emitter voltage at large collector currents. That is, like which is shown in the figure, the second breakdown voltage or a second breakdown occurs as a drop in the collector current and the drop in the output voltage. So there is one important factor or one important point regarding the second breakdown. which is called the current filaments. You should write it down. Current filaments. Okay, so the factor is the power dissipation is not uniformly spread over the entire volume of the device, and this leads to the formation of current filaments. Current filaments are the localized areas of very high current density. That is, the very high current flow occurs through certain points or certain regions in the semiconductor device. And once the current filaments are formed, there will be localized thermal runaway happening in that region, and the device will be destroyed. Okay, so that is the effect of second breakdown. And now we will see the saturation regions. Like we discussed, there are two saturation regions. One is the quasi-saturation, another one is the hard saturation. A quasi-saturation region and the hard saturation region. So the region between these two lines is called the quasi-saturation region, and the quasi-saturation region is a direct consequence of the drift region in the structure of a power transistor. So we know in the power transistor there is a n- drift region above the collector region. You can refer your figure, and if you want you can pause the video and you can go to your figure. So there is a drift region. Okay, so in the quasi-saturation region, normally what happens in the saturation region, both the junctions are forward biased. Okay, both base emitter junction is forward biased and the collector base junction is also forward biased. But due to the presence of the drift region, there will be some minority charge carriers which will restrict that forward biased situation, or that will restrict the saturation, actual saturation. Okay, so that is what happens in the quasi-saturation region. And in the hard saturation region, the normal saturation occurs where both the junctions are forward biased, because all the stored charges in the all the stored charges in the n- region is removed. Okay, so that is what about the hard saturation and quasi saturation. Okay, now we will see some features of that. So in a power electronic circuit, the power transistor is usually employed as a switch. That is, it operates in either cutoff or saturation regions. So we know that a transistor is operating as a switch in its cutoff and saturation regions. So the operating characteristics of a power transistor differ significantly from an ideal controlled switch in the following respects. It can conduct only finite amount of current in one direction when it is on. So during the initial classes, during the first class, we discussed for an ideal switch, when it is on, it should conduct infinite amount of current. But that is not the case of power transistor. Only a finite amount of current is transferred when it is on. And then it can block only finite voltage in one direction. So an ideal switch can block infinite voltage when it is off, but that is not the case of a power transistor. And then it has a voltage drop during on condition. So that is a major point. There should not be any power dissipation or voltage drop when it is on. That is for the ideal case, but for the power transistor, there will be a voltage drop during the on condition. Next point, it carries a small leakage current during the off condition. We know it is a semiconductor device when it is forward biased. So the cutoff means, or the turn off means, it is reverse biased. And of course, during the reverse biased condition, there will be a small reverse current. So there is a small leakage current during the off condition. The next point is switching operation is not instantaneous. That is when it takes time between the transition from on to off state. Okay, and it requires non-zero control power for switching. That is, it requires certain amount of power for switching. So these are the topics, or these are the portions covered in this lecture. I hope you have taken notes, and I will ask questions in the quiz from this video. Thank you.